talk about equilibrium. This one should be short and sweet. Equilibrium. Everybody's favorite topic. Yes, I said the same thing about redox. Let's use this example. All right. Whoop. Let's bring this down. This is the Haber process. This is how to produce ammonia. I know, Kelsey, it annoys you when I write NRG, but you'll survive. This is an exothermic process because energy is on the product side. Energy is produced. So, equilibrium. There are a few ways to shift equilibrium. The first one doesn't shift equilibrium, but I'm going to talk about it first because of that. Catalysts. Adding a catalyst. It lowers the activation energy. Therefore, it speeds up both reactions equally. It speeds up the forward reaction and it speeds up the reverse reaction. Therefore, it has no effect on equilibrium. No effect. CT, I think. Let's say all of these are gases as well. Okay, so catalyst has no effect. Increasing a reactant. Okay, so if I increase the concentration of the reactant, increase reactant concentration, it's going to shift it to the opposite side. So if I add more raw materials, I can produce more product. That should make sense to you. It should make sense to you that if I keep giving you bologna and bread, I can make more and more sandwiches. So if I increase the concentration of, let's say, N2, for example, that's nitrogen gas. If I add nitrogen gas, it's going to shift it to the opposite side. So my NH3 is going to increase, and my H2 is going to get used up because I have to use the rest of it to produce more NH3. So that's going to decrease. If you subscribe to this water theory, this water visualization that a lot of you seem to have liked this year, equilibrium is when these two things are balanced. We've got products on the right and reactants on the left. So here are my products, here are my reactants. That's a nice equilibrium. Okay, when I add more reactant and I raise the water level on this side, it's going to spill over to the products in order to reach a new equilibrium. So that's what happens. If I increase a reactant concentration, it's going to increase the concentration of the products. If I increase, for example, the concentration of H2, my NH3 would still increase, and my N2 would be used up, and it would decrease. Okay? What happens if I remove, I'll do this in a different color because it goes the opposite way. If I remove a reactant concentration, so if I lower its concentration, if I take away, if I decrease it, so instead of this arrow up by nitrogen, I'm going to put the arrow down, and I'm going to say I'm going to decrease my nitrogen concentration. Well, let's go back to this water analogy. My reactants and products were nice and balanced, but now I'm going to lower the reactants. Okay, so I have more on the product side than I do my reactant side. If I remove from some reactants, it's actually going to shift back towards the reactants to reach a new equilibrium. Okay, that's the only way I can shift these two things to reach a new equilibrium. So it's going to shift the opposite way. It's going to shift towards the reactants. My NH3 volume, my amount of NH3 is going to decrease, and my amount of H2, or my reactants, is going to increase. Okay? Same thing happens if I were to remove a product, but it would be on the product side, so it would go the opposite direction. So let's say I remove product. This is actually something that a lot of large chemical companies employ. They actually do this. They remove the product in a chemical reactor so that they can shift the equilibrium towards the products and produce more. So if I remove, in this case, NH3, or if if I remove energy, because energy, as you can see, up here is a product. So if I remove the NH3, it's going to shift it to the reactants. Going back to the water, I've got a nice equilibrium. Here we are. But if I start removing product and I put my water level way down there, excuse me while I erase it and redraw all these different colors, I have to spill more reactants over to the product side in order to make that balanced again. Okay, so my NH3 concentration here is going to go up, and my reactants are going to be used up. So that means my H2 is going to go down, and my N2 is going to go down. They're going to be used up so they can produce more product to reach a new equilibrium. Okay? That's removing product. Increasing a product concentration is going to cause it to shift back towards the reactants. So if you increase on either side, it's going to shift to the opposite side. If you decrease on either side, it's going to shift to that side, to the side that you decreased on. Let me rewrite this equation. I should have typed it, but I didn't, so bear with me. 3H2, arrow, arrow, 2NH3 plus energy. Two more things we need to talk about. First one is temperature, and then we're going to talk about pressure. Temperature is energy, okay? If I increase the temperature, both reactions speed up. That should be obvious. Increasing the temperature equals more collisions, equals both reactions speed up. However, how does it affect the equilibrium? If I increase temperature, let's make it red, because that makes you think hotter. And I'll do blue for decrease. How's that sound? All right, love colors. If I increase temperature, I'm going to increase the energy term wherever it might be. If it's an exothermic reaction, it's on the product side. If it's an endothermic reaction, it's on the reactant side. If I increase temperature, let's draw this little water balancing act again. Products and reactants. If I increase temperature, I'm adding to the product side. Ooh, that's a good color. Okay? So it's going to spill towards the reactants. So if I increase temperature, in this case, my NH3 is going to decrease, my H2 is going to increase, and my N2 is going to increase. The overall shift is going to be away from that increase in energy. If I decrease the temperature, it's going to be written here in blue. I'm taking away energy. I'm taking away a product, if you will. So in my nice little drawing here, I'm taking away, so I have to spill towards my products. So in this case, my equilibrium is going to shift to the right. My NH3 is going to increase in concentration. I'm going to produce more of it. I'm going to encourage the reaction to go this way to reach that equilibrium balance again. My H2 is going to be used up, and my N2 is going to be used up. Okay? So treat energy like it's a reactant or a product. Okay? Energy and temperature. Pressure affects gases only. I can't stress that enough. And I hope that none of you messed this up on the Regents. It affects gases only. Okay? Increasing the pressure is going to shift to the side of the fewer moles of gas. So towards fewer moles of gas. An increase in pressure goes to fewer moles of gas. So a decrease in pressure goes towards more moles of gas and has the opposite effect. Okay? Why does that happen? It happens because the more moles of gas you have that magic number of 22.4 per mole. The more moles of gas, the more volume. As I increase my pressure, I'm going to take up less volume. So in the case of this reaction, all of these are gases. So I have 1 plus 3, I have 4 moles of gas over here, and I have 2 moles of gas over here. So an increase in pressure is going to shift the reaction to the right, towards the products. A decrease in pressure is going to go towards more moles of gas, which is the opposite direction. Okay? What really is important is that you understand that. Now, I've talked to you about these before, these real-life applications. If my job is to produce as much ammonia as possible, what am I going to do to fully optimize this reaction so that my equilibrium shifts as far to the right as possible? Well, I'm going to probably do it under a really high pressure so that it tips towards the products. I'm going to make it really cold, and I'm going to pump out let's do this in green. I'm going to pump out as much energy as possible because that increases my products. Let's look on the other page. I'm going to increase the concentration of my reactants, my N2 and my H2, and I'm going to remove my product. All of those are going to cause my reaction to push towards ammonia.